Continue on here in this chapter. Chapter that is. I feel like it's 20. 20 seems like a nice number. I don't know, maybe. And we're talking about really transition metals. Then we got into coordination compounds. And coordination compounds, as we talked about, are really sort of like ionic compounds in a sense that they do have a cation and an anion, so a positive and negative sort of ion that's there. And they're really made up of two things. They're made up of a counter ion and a complex ion. And remember that you could really have any sort of combination of that. You could have a positive counter ion, and you could have a negative complex ion. You also could obviously have the other combination there, positive complex ion and a negative counter ion. And when we write formulas for coordination compounds, and also when we give the names, we do always go positive guy first, followed by the negative guy. And we got into sort of the naming aspect of these guys, and there are some interesting sort of rules that we do. There are the ligands that are attached, and we do, in terms of the complex ion part of the name, we do go ligands first in alphabetical order, regardless of prefix. We always go with the metal name at the end of it, along with the appropriate sort of Roman numeral. And then again, the counter ions are essentially just named like normal. So if you have kind of like a metal up front and it's positive, then you would just use the name of the metal, regardless of how many you have. If you have an anion like chloride or something like that on the back end, you would just call it chloride again, regardless of how many you have. And also, if you have more like a polyatomic ion as a counter ion, you would just use the name of the polyatomic ion. So we're right in the middle of that. So let's just kind of go over these rules one more time. Again, just make sure everybody's on the same page. As I just mentioned, we do go cation, then anion, both in name and formula. Our ligands go alphabetical order again, regardless of prefix. Now, there's some unusual names or certain names that we use for certain types of ligands. For example, water's aqua or aqua, carbonyl, amine for ammonia. If we do have several ligands of the same type in a complex ion, we do use prefixes like di, tri, tetra, penta, hexa for 2, 3, 4, 5, and 6. If the ligand itself does actually have a prefix in the name, then we would actually use a different set of prefixes, bis for 2, tris for 3, and tetrakis. So that ethyl endyl diamine, which is that one that we abbreviate with an EN, that's this guy here. This is the bidentate one where it could bind in 2 spots per molecule to the metal. Because that is ethyl endyl diamine and has the word di in the actual name of the ligand itself, that would definitely be a case if we had more than 1, 2, or 3, or however many, we would use the sort of bis or tris one. The other one as well, which is oxalate, which is oxalato, again, is also sometimes people will use that because of it being more like a bidentate sort of ligand, even though it doesn't necessarily have a sort of prefix in the name. So for that one, you could kind of go either way. And sometimes people will use the bis or tris, but I'm okay if you use di or tri. So you kind of go either way on that one. We do always, in terms of the metal, it always comes at the end of the complex ion part of the name. Again, that doesn't necessarily mean that will be the last part of the name. This would be kind of the middle part of the name if it's a positive ion, and it would be the last part of the name if the complex ion is negative. Speaking of that, we do use Roman numerals to indicate the charge on the metal. And as I mentioned last time, even for things where we normally do not use Roman numerals, like zinc, cadmium, and silver. We actually do still use the Roman numerals here for that. And as I also mentioned, it is possible to hit a neutral sort of metal that has kind of no charge. So kind of like not really a Roman numeral, but like a parentheses and zero is sometimes used as well for a neutral metal. Now, remember, it's important to understand whether or not your complex ion, which is typically the guys in the boxes, when you look at a formula, is positive or if it is negative. If it is a positive complex ion, then in terms of the transition metal name, we just use the regular old name like we normally do, iron, copper, whatever it may be. If the complex ion is negative, then we do use more of the sort of old school name for the metals, and those are typically the ones that end in ate, like ferrate, cuprate, stannate, all those type of names are typically what we use. Again, we looked at some of these, I think. So again, some of the names for our ligands, again, fluoro, chloral, bromo, iodo. That's typically what we use for an organic chemistry as well. Hydroxo, cyano there for cyanide. Here again is some of those older school type names like ferrate, cuprate, plumate, argitate, arurate, and stannate for silver, gold, and tin. And again, a few of those other ones. Again, carbonato in case you got carbonate, oxalato in case you have oxalate. Again, that is one where they sometimes will use that other sort of prefix. This is our EN here. And as I mentioned last time, we do use EN both a lot of times in the formula and the name. So if you don't want to write out the formula, you can just use that in there. And this is really EDTA, which is that guy that will combine in 6 places to trap the metal and sort of its name as well. So I think we did a couple there that we looked at the end. So why don't we do this one? Why don't you do the name of this guy and see what you come up with? When we look at this sort of formula here, I automatically, because of the brackets here, and it does have a transition metal, that does tell me that this is my complex ion parts. Usually the guys in the brackets, definitely what a transition metal is. That would mean that up here up front is going to be my counter ion. And really just from the location of each of those things in the formula, I know my counter ion is going to be positive and my complex ion is going to be negative, as that's how they should go. That also tells me that in terms of the metal here, we need to roll with kind of the old school name here because the complex ion part is negative. Before we do that, we also probably want to figure out what is the oxidation state on that transition metal. So if we do that, we'll take a look here. We have oxalate, which is -2 each, and there's 3 of them. That gives you like a -6 happening there on the oxalate part. Potassium is +1, and there's 3 of them, which gives you a +3. So +3 and -6 is -3. And that means that the chromium here would be carrying a +3 oxidation state. Any question on that there? So that means we do know that it is negative, and that will give us chromate, as we need to go with the ATE version of it, and a Roman numeral 3. We also have 3 oxalates. And again, in terms of how we name oxalate, if we kind of take a peek back here, that is our oxalato is the name that we use for oxalate. And because there are 3, we can go with trioxalato. This is also one, like I said before, that sometimes people will use the tris oxalato. And again, for us in here, you could go either way. And whoops, come back there. Now we pretty much have all the components that we need. We could start with our counter ion in this case. And once again, the counter ion is pretty much just named the element in this case, which is a metal. So that's going to be potassium. When we get to the complex ion part, we do go ligands first with the metal coming at the end. So that would be potassium trioxalato, chromate, Roman numeral 3. Or again, if you want to use the other guy, a little potassium. And again, it's just for oxalate, sometimes people will use that sort of tris for it. In this case, chromate 3. Now, again, when we look at the formula here and we look at just the complex ion part, CrC2O43, this is -2, -6, +3. That means, again, our complex ion here is carrying a -3 charge. That is why we have not 1 potassium, not 2 potassiums, but we have 3 potassiums to balance out the -3 charge there for our counter ion in this particular case. By the way, the coordination number here would be? Coordination number here would be 6 in this case, as oxalate can combine in 2 places per molecule. It's bidentate, and there are 3 of them, which means the 2 oxygens in each of the oxalate that are single bonded will bind to the metal, which gives you 2, 4, and 6 atoms that are directly bound to the metal, and that will give you a coordination number of 6. I think maybe we also had something that looked like this, which you can also combine with normal sort of naming. So if you had something like this, which is a hydrate, and that is what a hydrate is, right? Where you have the little dot and some waters attached to it. You basically would roll the same way and pretty much call it the same thing. This would be potassium trioxalato chromate 3. And hydrates are named based on prefix and water. So prefix for 3 is tri and hydrate for water. And if it was a hydrate form, you would just add the trihydrate at the end of it. Any question on any of that parts there? Okay. I think I said last time the names go on and on and on. The big screen. All right, let's try a couple more here. Top one name and bottom one formula. Here's another table of some more metal names in terms of the old school tape names, in case you need them. Okay, so let's take a look. We'll start top one here. Once again, we see these brackets, also a transition metal there. So that is our complex ion part. This is going to be our counter ion in that case. Once again, we see based on location, complex ions should be positive. Our counter ion in this case is going to be negative. We'll do a little bit of oxidation state there on the chromium. Water is 0. Each of the CLs, there's -1. There's 2 of them, gives you like a -2. We also have a -1 on the outside there, so that's a -3. That means in this case, our chromium is going to be +3 once again. And in this case, because it is a positive complex ion, we could just use chromium, the whole name there, no fancy name, and Roman numeral 3 that we got going. We have 4 waters. So 4 is tetra, and water is aqua or aqua, your choice, whichever way you want to go. We also have 2 CLs also attached. Prefix for 2 is di, and Cl would be chloral in that case. So that pretty much takes care of all of our complex ion part. So we do need to put it together here. Again, we're going to go ligands first on the name, regardless of prefix. So we're actually going to compare A to C here, and it's going to be the A first. So this would be tetra aqua or aquo, dichloral chromium, Roman numeral 3. And again, our counter ion here is going to be named like normal. This would be chloride in this case. So tetra aqua, dichloral 3 chloride. Again, if we sort of look at the we look at just the complex ion part, this again is basically -2 and +3 and 0 Overall, our complex ion has a +1 charge, and that is why we only have one Cl, which is Cl minus, to balance it out in terms of our counter ion. Coordination number on this guy is? Coordination number on this guy is 6 as well. It's got 4 waters directly attached and 2 chlorines. They're all monodentate. They will all bind to the metal 1 time each, and that's a grand total of 6 in this case. Any question on that one there? All right, so we have the name. We're going to kind of put it together. So tris, ethyl endyl diamine, and again, this is why they are using tris, because the ligand itself has the di in it. So instead of tri, they're going to use tris. Tris means 3. This is the one, as I mentioned before, you're more than welcome to use En in formulas, which is very common. So we have 3 of them. If you would rather, you could also just use the actual formula, I suppose, if you wanted to, and write it in there. That takes care of that part of it. We have a cobalt with a Roman numeral of 2, and that obviously through this part of it is our complex ion. I know that is my complex ion because that part ends with the metal at the end of it, and the Roman numeral, it also comes first, which means I know my complex ion is positive, and it's also the regular name, which also tells me my complex ion should be positive. So putting this together, we got a little cobalt, we got a little En and a 3. The reason we should probably maybe figure out our charge here is, again, this is 0, this is +2. That means that +2 is my complex ion charge. The sulfate here is my counter ion, and that is good because -2 and +2 means I really only need one of the counter ion, which will give me a coordination compound that looks something like that right there. Any questions on that one there? Coordination number on this guy is? Coordination number is, it is 6 as well. Again, bidentate here. So each of those nitrogens are going to bind. So 2 per molecule. There's a total of 3 of them. So you'll have 3, total of 6 atoms directly attached to the metal. Any question on that there? All right, a couple more here. Now you're getting the hang of it and enjoy. Okay, so let's take a look and see how we're doing. Once again, here I see complex ion part first. Also tells me it's positive. This here would then be my counter ion happening. Again, looking at charges here, NH3 is 0, is not ammonium. This is ammonia, no charge. -1 there. We got a -1, and there's 2 of them. So on the outside, so we do have a -3. So our cobalt here is going to have an oxidation state of +3. In this particular case, then we could go with cobalt Roman numeral 3 for our metal part, since our complex ion is positive. We do have 5 of the ammonias. 5 is penta, and that is amine for the ammonia. We also have 1 Cl also attached, so that is a chloral, and that's pretty much all of the complex ion part. So again, we're going to go alphabetical order first, and that would put the A here before the C. And again, ignoring prefixes, so this would be penta, amine, chloral, cobalt, Roman numeral 3. And our Cl2 here is just going to be called chloride, regardless if there are 2 of them. No prefix or anything on that. We just call it chloride in this particular case. We are looking at a complex ion that is positively charged, and that is going to be a +3, a 0, and a -1. That is a +2 charge on the complex ion. That is why we have not 1, but 2 of these counter ions again here to balance it out. Coordination number here would also be 6, 1 there and 5 there. Yes, those are all directly attached to the transition metal in the complex ion. Any question on that one there? Looking at the bottom one there, we see counter ion first, which means it's positive. This is our complex ion here, which means it's negative. Looking at the charge, that is cyanide, which is -1, and there's 6 of them, gives us a -6. We got a +1 for the potassium. There's 3 of them, gives us a +3. So that is going to hit us with a +3 on our iron. Because our complex ion part in this guy is negative, that means we got to roll with ferrate instead of iron. And we still need the Roman numeral of 3. We do have 6, which is hexa, and cyano there for our cyanide. And that's really our complex ion part. For our counter ion, we just name it. So that's going to be potassium. Again, we're going to go ligand first. Hexa, cyano, ferrate, Roman numeral 3 here. Again, counter ion, complex ion deal. Our complex ion in this case is carrying that's a -6 + 3, a -3 charge, which again is why we need our 3 positive counter ions there to balance it out. Any question on that? A reminder that we also talked about last time that if you just had the complex ion part, pretty much the name is just going to be this part of it, and then you would put ion at the end of it. So you would name it the same way, just kind of put ion at the end if you do not have a counter ion. And same thing up here, if you just had the ion, it would be the front part of the name here without the chloride, and you would just put ion at the end of it. So if you have just a complex ion by itself without the counter ion, you do just name it the same way. Just leave off the counter ion and part of the name, and pretty much add ion at the end of it. Any question on those two there? All right, then here, a couple of formulas here. Okay, so let's take a look at this. Once again, look at this name. I know the front part of the name here is my complex ion. I know that for a couple of reasons. Again, the metal comes at the end. Metal is a regular sort of name. So that is our complex ion part. This would be our counter in this case. So if we just kind of get the pieces out of the name here. So triamine is ammonia, and tri is 3. So I got 3 of those. Bromol is bromide, and platinum 2 is a platinum with a +2 charge. So if I just sort of build my complex ion part of it, we'll roll with the metal, a little NH3 and a Br. Here I know this is -1, this is 0, this is +2. That means that the overall charge here on my complex ion is +1 from that. And that's important because when I look at my counter ion, which is chloride, which is -1, that tells me I just need one of those to kind of put it together and balance it. And then we could put it all together here, PT, NH3, 3, Br, and Cl, in this case. Any questions on that one there? Coordination number on this one would be? Coordination number on this one is 4. Yeah. 3 there and 1 there. Again, those 4 things are directly attached to the metal in this case. They're all monodentate, which means they bind in one place per molecule. Looking at the next one, I know that this is my counter ion. And I know that, again, because I see the metal at the end of the name on the second part. And I also see the kind of the old school name there, which means that this is going to be my complex ion. So I do know my complex ion is going to be negative in this case. And again, if we just kind of build our complex ion part, I got hexa, which is 6, and fluoro, which is fluorine. So I basically got an F6. Takes care of that. I got a cobaltate, which is a cobalt with a +3 charge because of the Roman numeral. So if I build my complex ion part, I got a cobalt. You don't really need parentheses around the F unless you like to. That's going to give me a -6 and a +3, which means my complex ion here is actually carrying a -3 charge. And again, that's important because potassium here is the potassium ion, which is +1. That means in order to balance out the charge, I need 3 of those guys. So putting all that together, this should be a K3COF6 type of situation happening there. Any questions on that there? So you do need to be able to obviously name these, write the formulas, figure out the coordination number, and also figure out obviously the oxidation state on the transition metal. Any questions on how to do any of that there? Okay. All right, then let's talk a little bit about some other properties here of complex ions. The first thing we're going to talk about is isomers. And isomers are essentially things that have the same formula, but sort of a lot of times some type of different connectivity in three-dimensional space. So although they do contain essentially the exact same number of elements, the exact same elements, because of the differences in their arrangements, they create isomers and they'll have some different connections. And that will also give them some different properties depending on that connection. So in terms of isomers, there are structural isomers, which have different bonds. And sort of underneath that type of isomer, there's a coordination isomer and a linkage isomer. And we'll talk about each of these separately in just a second here. Also, isomers can be classified as stereoisomers, which have the same bonds but really different arrangements in three-dimensional space. That could give rise to geometric or cis or trans isomers, and also optical isomers, which have the ability to sort of bend polarized light, plane polarized light one way or the other. So let's take a look at each of these different types of isomers and talk a little bit about the differences that we see. The first one is a coordination isomer. So again, if we sort of compare both of these coordination compounds, they have the exact same elements present. So we got one chromium, excuse me, one chromium, 5 ammonias, a sulfate and a sulfate, and a Br and a Br. So they contain the exact same things. The difference is, though, in the first one, this is our complex ion. And what that means is in the first guy here, the chromium has the 5 ammonias attached to it. Through the nitrogen. And in this case, it actually has the sulfate attached as well. And that's going to create a overall +1 charge, with this being +3 in this case. And sulfate being -2, all the rest of them being 0, because it's +1. And our bromide here is actually acting as the counter ion. So it is not really attached to the complex ion in this case. And that is different than what we see on this coordination compound. Here, that is the complex ion part. And we have our chromium in the middle. Also still has the 5 ammonias attached to it. But here we actually have the bromine directly attached to it. And that gives us a +3 -1 overall charge here, +2. And it is the sulfate in this case that's actually acting as the counter ion. So although they both have a coordination number 4, they both have the identical sort of elements present in each of them. There is a difference in sort of where the bonds are happening here. In the case of the first one, the sulfate's actually part of the complex ion. And in the second case, it is the bromine that is part, or bromide that is part of the complex ion. So that is a coordination isomer. We're typically speaking, you get that sort of swap out that happens. One of the ligands becomes the counter ion, and the counter ion becomes part of a ligand. And again, that's the difference there in the coordination isomers. Any question on that there? Now, the next type of isomer is a linkage isomer. And in this particular case, what actually happens is it is the same ligand that's attaching, but the ligand itself has the ability to actually attach via a couple different sort of elements. So if we look at our friend nitrite here, in the case of nitrite, it has the ability to attach to the metal through the non-bonding electrons on the nitrogen, but it also has the ability to attach to the metal through the oxygen non-bonding electrons. It is still going to attach in only one place, but it will attach either through the nitrogen or the oxygen here. And that's what we see here in the top one. It is the lone pairs on the nitrogen that is attaching to our cobalt. And in the second case, it's the same ligand, but we're using the electrons there on the oxygen again to bind to our metal there. Remember that when we look at sort of these complex ions, we do kind of think of them, as we talked about, as Lewis acids and a sort of Lewis base situation. Lewis acid being something that's electron deficient, will accept electrons, and those are typically our transition metals here with the positive charge. They are electron deficient, right? Otherwise, they wouldn't be positively charged. And that makes them really good acceptors of those electrons. And obviously, our Lewis bases are our ligands here that have those sort of unpaired electrons, things that are negative, things that are polar, and have those unpaired electrons are really good sort of donators of electron pairs. So when we talk about a linkage isomer, again, it's the same ligand, just going to attach via a different element within the ligand, because it does have the option, like we see here with NO2, nitrogen or oxygen has the ability here to actually bond into that. Any questions on that? And that's because if we really do draw sort of our NO2, right, minus a little old school Lewis structure action, right, 5 plus 12 plus 1, so that's 18 valence electrons. So again, if you were to draw it, 2, 4, 6, 8, 10, 12, 14, 18, and you would need to double bond. So what ends up happening in this situation, get rid of those, is it again has the ability, because this is asymmetrical geometry, polar with the non-bonding electrons there, and through the single bonded one, again, has the ability basically to bind into the metal in that particular case. Again, they will not both, in this case, do it together. It'll be one or the other, and that's what creates these different sort of isomers depending on how they bond in. Any questions on linkage isomers there? All right, so let's talk a little bit about stereoisomers. Stereoisomers are geometric isomers that can create cis or trans. And when we talk about cis and trans, you oftentimes talk a lot about it in organic chemistry. But cis basically means the same side, and trans means opposite sides. So when we talk about sort of it in organic chemistry, which maybe we will, I don't know, we'll see. A lot of times we talk about it in terms of the double bond. And again, if we have groups sort of on the same side of the double bond, that would be cis. If we have groups on opposite sides of the double bond, that would be trans. When we talk about it in terms of these type of complex ions, oftentimes we're talking about it in terms of like the plane of the molecule, for example. And there's a certain sort of plane of the molecule, and we could have groups sort of on opposite ends of the plane of the molecule, and that would be trans, kind of one above the plane of the molecule and one below. And we could also have, for example, a situation where, we have, those same groups on the same sort of side of the plane of the molecule, and that would be cis of each other. So atoms that have the same bonds but different bond angles, these are common in square planar complexes. Remember, square planar is the one that makes like a square, sort of the expanded octet. When you talk about sort of geometry that you did there, it's one of those ones that is actually a symmetrical arrangement because they all sort of cancel out into a square. So if we look at this here, square planar is a coordination number of 4, by the way. 1, 2, 3, and 4 here with the nitrogens binding there on the NH3s in this case. But when we look at the NH3, for example, if we think of this obviously as the plane of the molecule here, we could see that the NH3s, for example, are on the same side. And even the Cls you could look at are also on the same side. And this would be cis. And that is different when we look at this guy here, also coordination number 4, also square planar. We see that the chlorines, for example, are on opposite sides of the plane. And you can also, again, look at the NH3s in this case, and this will give you the trans isomer. So the cis or trans isomer will have some different properties because of the arrangement of those groups. Just simply here, you can see one is yellow, one's a little lighter yellow in terms of color. And again, we're talking about cis, same side, or trans, opposite side. We could also see this in a coordination number of 6, which is what we see in these two guys. That is our friend octahedral, if you remember. 6 electron pairs, a little octahedral geometry happening there. And in this case, we have, again, you could kind of think of it as the plane of the molecule. And when we look at the chlorine, it's above and below the plane of the molecule there. And those would be on opposite sides of each other. And that would be trans. And again, you can kind of see here above and below the plane of the molecule. Here at this guy on the right, they are kind of like 90 degrees of each other. They're kind of on the same side of the plane of the molecule there, and this would be cis. And again, sort of that will happen if you got somebody at one of the corners and the guy up, or even the guy on the bottom and one of the corners would also be cis. You know, they're both on the bottom side of the plane of the molecule. So in the case of a coordination number of 6 in the octahedral geometry, usually the trans guys will be on that opposite sort of above and below. And again, they'll be sort of on the same side of that plane if they are on the cis. Now, optical isomers have opposite effects on plane polarized light. There are molecules that have non-superimposable mirror images, and those are what are sometimes referred to as chiral molecules. And these isomers are also referred to as being enantiomers, which are chiral as well. So what does that mean? As we will see shortly here, but we'll just basically look at it here for a second. Basically, what that means is if you put a molecule up to a mirror and the mirror image is reflected, and you grab that mirror image and you take it out, you will not be able to superimpose it on the original molecule and everything will fit correctly. So the simplest example of a chiral sort of situation or molecule is your hand. If you put this hand up against the mirror, you get this hand reflected back to you. And if you pull out your mirror image, you can do whatever you like. You can rotate it without breaking your hand or anything like that, but you'll never be able to get these things to sit correctly. Although my thumbs are good here, palm up, palm down is not correct. If I flip it this way, I got palm down, but my thumbs are on the wrong side, right? So even with rotation, if you have a chiral molecule and you pull out that mirror image and you rotate it, you will never be able to get it to sit correctly because there's always going to be pretty much a bond that is moved slightly in terms of its bond angle. And there will always be some type of bond that's just off. It just will not sit. You might be able to get 3 of 4 to sit correctly, but that fourth one is not going to sort of sit correctly because of the way the bonds are sort of reflected. Sometimes very hard to visualize those things. You can look at models, but unpolarized light consists of waves that vibrate in different planes. Polarized filters blocks all the waves except for those vibrating in a given plane. So for example, some of these molecules have the ability to rotate the light one way or the other. You could also measure the angle as it kind of goes through it. And, you know, can rotate it left or right in terms of that, giving us some different isomers like L or D. And there's our hand sort of example in terms of our mirror image. And again, you could try that yourself, but you'll never get it to work. So let's take a look at some examples of this. Here, we're looking at a coordination number of 6 in this case. and this is our octahedral geometry. And if we look at this, number 1 and number 2 are mirror images that cannot be superimposed on each other. So this is our sort of original structure here. And when it gets reflected in the mirror, it's going to reflect, right? It's going to reflect. It's going to kind of reflect. This guy is going to reflect. And then this guy is going to reflect in the back. So what ends up happening if we sort of blink the screen, unblink the screen there. Let's try that again. What sort of ends up happening is this bond, as it gets reflected right here, this bond between the nitrogen on the bottom and sort of the corner guy actually gets reflected to the back. So this nitrogen basically gets reflected to the back part. And what that creates is a different bond in the mirror image that this guy doesn't have. It's obviously a much shorter bond than the original guy. But once it gets reflected and you pull it out, you will have this location of this bond between those two nitrogens, which is never going to sit right in if you locate it, because now it's at a sort of a different bond angle than where it was originally. So that small little variation as that thing gets reflected in the mirror image, it carries its bond over, but now its bond is between here and here versus between here and here. So as you try to rotate that, again, that bond is always going to be just not in the right position for it to be able to sit correctly in place. Now, if we look at the guy over here on the left, this is trans guy here, also coordination number of 6. But when this gets reflected in this transpositioning, everything gets reflected okay, because now these two bonds are still going to be in the same spot. When this guy gets reflected here and this guy gets reflected in the back, they still have the same bonds as the original guy does as they reflect themselves in that mirror, which means this guy, if you do pull out the mirror image, you would be able to get it to sit correctly on top of the original guy, because really no bonds have sort of moved within the mirror image as it gets reflected. Usually, if that's a situation, that's sometimes referred to as an achiral sort of compound. An achiral compound is one where you can take the mirror image out, and even with sufficient rotation, you could get it to fit correctly on top of the original guy. Here again is our cis, which typically cis have a little trouble when they go into the mirror image. They get that sort of swapped out bond. And again, if we reflect here, this guy is going to go here. This guy is going to go into the back. And this guy is going to go here. So that again is going to move that bond like we saw earlier to kind of the bottom to the back, as opposed to the bottom to the front on this guy. And again, that's going to create that difference in that bond. And this guy would be a chiral guy on the right-hand side here, as those bonds will not perfectly overlap with each other. So trans, oftentimes you'll be okay because they're on opposite sides. So when they reflect opposite, right? So you get the same bonds that happen. Cis are on the same side. So when they reflect, we get some switching of some bonds that occur in this situation. So the bottom guy there on the right is a cis isomer. Mirror image is not superimposable, and thus these would be considered optical isomers of each other. These two guys here, this guy and this guy, would be optical isomers of each other, which could rotate that plane polarized light. So two molecules that are mirror images of each other and non-superimposed mole are again called enantiomers. A lot of biomolecules are chiral. A lot of drugs are as well, but only one of the isomers, again, because they do have different connectivity, does actually affect some of the properties of it. So even though they may be exactly the same in the sense, because of those different bonds that sort of develop, they may not have some the same properties or overall the same properties. Any question on isomers here? So let's talk a little bit about bonding, is more specifically what happens with the electrons in the transition metal. And as we know, transition metals are d electrons, right? That is what they are. They have pretty much. And those are really where all the electrons are pretty much going to end up. And what I mean by that is when those metals accept the electrons, they're able to accept them into those d orbitals, electrons, because they have them available to them. So the formation of hybrid orbitals to share electrons, you remember hybrid orbitals, that's a little sp, sp2, sp3 action, little sp3d, sp3d2. These correlate to certain geometries like linear, right? Trigonal, planar, tetrahedral, triangular bipyramidal, and our octahedral, right? So Vesper models doesn't work very well for complex ions. Again, as we've been talking about, we really sort of think about it more of that Lewis acid base situation where we're donating and accepting electrons into these d orbitals. The hybrid orbitals used by metals does depend on the number of ligands, and how the electrons are distributed also depends on sort of which ligands are present when you look at it. So just a reminder, some of these geometries, when we look at this sort of coordination number 6, which would be sp3d2. By the way, if you just count up all the letters, that is 6, right? 6 electron pairs, coordination number 6, basically. That is our NH3 donating the electrons into these d orbitals of our transition metal as they come in. And again, because they have the d orbitals, they have available to them a way to bond, right, and accept some of those electrons that are coming in this particular case. Here are some of the geometries that we sometimes will see. That is our tetrahedral, our sp3, coordination number 4. This is also coordination number 4. That's our square planar, our sp3d. And this is sp, which is linear, which is a coordination number of 2. And that is typically will give you that linear geometry that occurs. And speaking of that, there is sort of typical geometries that kind of correlate to coordination numbers. So as I mentioned before, 2 is linear. 4, coordination number 4 can actually be 2 sort of geometries. It can be your kind of normal 109.5 tetrahedral arrangement, kind of like 4 electron pairs. That would be more like an sp3. This is your square planar, which again is your expanded octet, which also would be a coordination number of 4, both of those guys. And typically speaking, a coordination number of 6 will involve the octahedral geometry. And again, an easy way to remember that is octahedral 6 electron pairs, coordination number 6. Tetrahedral is 4, 4. Linear is 2 electron pairs, so coordination number 2. Square planar is the only one you got to think about, I guess, in that sense. So what happens with these electrons when we start to have ligands attaching to our metals? Well, first off, as you hopefully know, there are 5 different d orbitals. These are the 5 different d orbitals available to our transition metals. And in the absence of any ligand being present, these d orbitals are all basically equal in energy. Once sort of ligands get in place, there's actually a change that occurs in terms of the energy of these d orbitals. And there's actually what is referred to as splitting of these d orbitals. And when we look at this idea here, and by the way, we were specifically looking at here a coordination number of 6 and an octahedral arrangement is what we're looking at here in this particular example. In the presence of a ligand, we'll get this crystal field splitting, which is sometimes abbreviated with a delta. It's also a change in energy, h times the frequency, Planck's constant times our frequency. Right, Planck's constant being 6.63 times 10 to the minus 34 joule seconds. You might also remember C is equal to the wavelength times the frequency, where the frequency is equal to C divided by the wavelength. And that means that you could actually calculate the crystal field splitting by using some equations that you've seen before, probably. And C is the speed of light, which is 3 times 10 to the 8 meters per second. Lambda is the wavelength in meters. Yeah. So if you know the wavelength or you know the frequency, you could figure out the energy. So the crystal field splitting is the difference in energy between the lower d orbitals in this case and the two higher d orbitals. So this crystal field splitting is that energy difference between those. So why does this affect things? As you know, hopefully electrons, when they go into orbitals, go in one at a time, right? And then they come back and start pairing up. They also go in lowest energy first, right? Until that's filled, and then the next lowest energy, and then the next lowest energy, and they kind of fill that way. So what happens in this situation is, depending on the ligands, for example, that are present, you may end up with a splitting that is what is sometimes referred to as weak filled. Not very big difference in energy between those lower guys and upper guys. So sort of a small difference. And that means that when electrons come in here, they will decide, well, no big deal. That's a little bit up there, but not such a big deal. We'll just kind of feel like normal. And then we'll come back and sort of pair up. Now, there is a situation, as we'll talk about, where you could get this splitting between the lower guys and the higher guys that is relatively sometimes referred to as strong filled, which is a much larger sort of split in energy. And the problem with that, or the consequence of that, is as the electrons go in, they're going to decide that's like way too high in energy. I much rather kind of pair up down here until I'm forced to make my journey up there. So what this is going to sometimes happen with these complex ions is it will create what is sometimes referred to as a high spin complex because it has a lot of unpaired electrons, very paramagnetic, versus something that is sometimes referred to as a low spin complex, which has a lot more paired electrons than unpaired electrons. Any questions on that there? So when we do this, as I mentioned before, we could use this formula that you've seen previously. And as we've done before, when we do take an absorbance value, we do set the wavelength right to the maximum wavelength of absorption. That way, all of our samples, right, do get to be on scale. We wouldn't want to choose a wavelength way over here. We also know, as we talked about, right, that the light or the color of the solution that we see is complementary to the color of light that's being absorbed, right? So that's why we do set our wavelength to say different than the color of the solution, because that will give us our maximum wavelength. So we can actually calculate, for example, the crystal field splitting if we know, for example, the wavelength at which this complex ion absorbs. So for example, if we look at this guy here and we have this sample that absorbs at 470 nanometers, this is a coordination number of 6, which means we're going to get that octahedral splitting. And when we look at it, we want to know what color is the complex. So we know 470 would be in this ballpark. And again, it would not be blue. It would be absorbing blue, but to us, it would look orange as we go with the complementary color wheel over here. That's why when you have the red samples, you set it more in the greenish area when you set your wavelength when you're doing that because your sample solution was red. So we could actually use our E is equal to hc over the wavelength. Both of these guys are constants, so that is Planck's constant right there. That is our speed of light. Because our wavelength does need to be in meters, we know that 1 nanometer is 10 to the minus 9 meters. So that is the conversion down here. And that will get us our meters canceling out, our seconds canceling out, and that will give us our energy per atom in this case. And if we wanted to know how much energy per mole, we would use our Avogadro's number. So we would multiply our Avogadro's number. So essentially you would be taking 4.23 times 10 to the minus 13 joules per atom. And you would take Avogadro's number atoms per mole. The atoms would cancel. And that would give us some type of splitting energy of about 255 kilojoules per mole. So it's very similar to a calculation you probably did in 200A at the very beginning of the semester. But again, you could actually calculate the value of the crystal field splitting if you know the wavelength or you know the frequency. Any questions on that there? So how do we know, are we going to get sort of a strong field or a weak field? It does have to do with the ligands that are attached. So this is the spectrochemical series. And on sort of the left-hand side here, that is weak field. And that means that when we get the splitting of these d orbitals, we are going to get a small difference between them. And that will lead to everybody kind of going in like normal, one at a time, before they want to kind of pair up. So that's going to give you a lot more unpaired electrons and a high spin complex. We got somebody on this side, that's going to lead you with a strong field, which is going to give you that larger splitting. And you most likely will have a lot more electrons paired up and give you that kind of low spin situation that's going to occur, or high spin. Now, what about the guys in the middle? Well, the guys in the middle, sometimes they will tell you, do it for the high spin complex or do it for the low spin complex, or they'll tell you, do it for strong field or weak field, and that will basically give you directions. Sometimes you may not even get any information. And a lot of times in those cases, it doesn't really matter. You could do strong field or weak field, and you'll end up with the same. For example, if I just had something with 3D electrons, no matter what I do, I could only fill up the bottom, right? It doesn't matter if there's high or low going up to the next one, because I only need to put 3 in there and they're all going to fit on the bottom. So it doesn't make a difference. So there are certain situations, if you're not given any information, that's probably the case. It won't make a difference which way you do it. If it's somewhere not sure, those oftentimes kind of give you information on how to do that. So to sort of show you how this works, if we take a look at this guy up here, and we want to look at nickel, which is our transition metal, and nickel is number 28 on the periodic table. And the electron configuration for nickel with no charge is 4s, argon 4s2, 3d8. So if we take a look at this guy here, we know that bromine is -1, and that's -6. There's a -2. That means in this particular case, our nickel has a +4 charge, which means when we go for the electron configuration for nickel with a +4 charge, remember that transition metals will always lose those guys first. Then they will lose out of the D, which means nickel will have argon 3d6. It is these 6 electrons that need to be distributed into your crystal field splitting. So when we look at this, this is a coordination number of 6, which is our octahedral splitting. And we do want to look at bromine. And bromine is a weak field ligand, which means when we get the splitting of the lower D guys and the upper D, we will end up with a weak field here, which is a small splitting. And when we go to distribute these 6 electrons, they will go in like this and decide, that is not too bad. And they will fill in like this. And this will end up with 4 unpaired electrons. And this would be considered a high spin complex. And those are typical questions that you're asked. How many unpaired electrons does it have? And is it sort of high spin or low spin? Any question on that one there? All right, so why don't you take a moment here then and work out the other ones here. Draw the crystal field splitting, figure out how many unpaired electrons you have in each of those. And iron is 26, by the way. And for this one here, we'll do high spin complex for this guy. Do it as a high spin complex. We're almost done, so we'll just kind of finish up the last couple of examples here. So we'll run a little long. Okay, so let's take a look, see how you're doing. So we'll look at the one underneath it. Again, En is 0. That is a +4, which means the nickel here is still +4 in this case. This is also a coordination number of 6, as that En is bidentate. And we do want to look at the En, and we do see it as closer to strong field here, which means we are going to get this separation, much larger separation. So we're going to still have 6 electrons to distribute. And those 6 electrons in this case will go 1, 2, 3. Decide that's a little too high. We rather fill up down here first. This is going to give us 0 unpaired electrons in this case, and definitely would be a low spin situation as we have a lot more paired electrons. We have no unpaired electrons in this particular case. Any questions on that one there? Now we're going to look at the FeF6. Iron with no charge is argon 4s2 3d6. And in this case, the iron, that's -1, -6, -3, -6. That's going to be a +3 for the iron in this case. Also, again, a coordination number of 6. So we're going to get this octahedral splitting. When it goes to iron with a +3, we will lose these 2 electrons and one of those electrons, which will give us argon 3d5. So in this case, we have 5 electrons that need to be separated. High spin usually correlates to a weak field, which means we would draw the guy on the left here, and we would distribute our 5 electrons like so. 1, 2, and they would go up because it's not that big of a split, and we would actually end up with 5 unpaired, right, electrons, and definitely a high spin complex. Question on that there. By the way, if we did this for a low spin complex, we would actually draw the guy on the right, and it would end up looking like that. Yeah, basically with 5 electrons, and it has 1 unpaired electron if they want you to do strong field or low spin. Lastly, if we look at the last guy there, that's going to be -1, -6, -3, also +3. So again, in this case, we still have the 5 electrons to distribute. That is Cn, which is strong field, which means I just did it just now, but we'll repopulate it here just to show it. We would draw the guy on the right here. And again, it would go in 1, 2, 3, 4, and 5. We would have 1 unpaired electron in this case, and that definitely would be a low spin 1 unpaired electron. That's again a very common sort of question for these guys is how many unpaired electrons? Would it be sort of high spin or low spin? Any questions on how to do that? You're basically distributing the d electrons from the transition metal in the complex ion. Any questions on that? All right, so here is the different combinations of high spin versus low spin. On the left there, you can see much smaller separation. And again, we have a lot more unpaired electrons on the left, a lot more paired up electrons there, diamagnetic on the right, giving us our low spin. And again, this type of splitting where we have those 3 on the bottom, those 2 on the top, is specific for a coordination number of 6 and octahedral geometry. Now, there are a couple of other geometries, and that is tetrahedral, and that is a coordination number of 4. It is pretty much the opposite of octahedral. The 3 that were on the bottom in octahedral are up on top, and the 2 that are on top are on the bottom. Works the same way. They would start to fill the bottom, depending if it's too big or not. It would go up or stay on the bottom, and pair up or go upwards and go one at a time. So coordination number for tetrahedral, basically the same sort of splitting, just reversed. Also for a coordination number of 4, which is square planar, you can see it goes a little crazy, everybody all over the place. But again, still kind of works the same. Lowest energy gets filled to the next one, to the next one. For us in this class, you will be responsible for octahedral coordination number of 6. And we'll do basically its opposite here, tetrahedral coordination number of 4. We'll leave the crazy square planar off of the map there. We won't touch that one. So out of those two, you do need to be able to draw the crystal field splitting diagram for octahedral or tetrahedral and be able to figure out questions like that. How many unpaired electron, high spin, low spin? Any questions on any of that there? All right, that wraps up this chapter.